Hello, I'm going to be giving a demonstration here of several ways to use Matlab and another computer program for solving statics problems. This will be a simple statics problem of equilibrium of a particle with three forces acting on it. I'll show GeoGebra.org just to get the geometry of the problem a little bit. And with Matlab, we'll be doing several different methods for solving the same problem. We'll use the law of sines. We'll use components. Components we'll do two different ways. We'll do a symbolic method and linear algebra. The problem here is, again, a ship unloading operation. There's a 3,500-pound automobile supported by a cable. A worker tied a rope to the cable here at A and pulls it to align the car where he wants it to land on the dock. Currently, nothing's moving, and the angles are given of the cable and of the rope. So, what do you know from this problem? Well, we know the weight of the automobile. We'll call that W. W equals 3,500 pounds. We know the angle of the cable right of vertical. Call that angle B equals 2 degrees. And we know the angle of the rope below horizontal from the picture. Let's call that angle A because it's close to the point A in our drawing. The main thing, though, to keep track of, and you should have on all your problems, is what is the question? Of course, find the tension in the rope. What are the tensions in the rope and the cable? So find the tension in the rope, and we'll name that TAC because it's tension in the rope and it's going from A to C. Likewise, we want to find the tension in the cable, and we'll name that similarly TAB because it's the tension going from A to B. So summarizing our given information and what we need to find, TAC and TAB. First thing we do in statics is almost always a free body diagram. So we want to look at the forces acting on the ring here at A, or the knot at A. And those forces, we can see the weight of the automobile is pulling down. We have the tension in the rope here pulling down at 30 degrees. And the tension in the cable holding everything up at 2 degrees from vertical. And this is, the ring is not moving, so it's in equilibrium. When we have something in equilibrium, we could, in our drawing, have used the names of these angles as well. But for equilibrium, we want sum of the forces equals 0. That's our main equilibrium thing. And we're going to use a force triangle by moving all of the forces tip to tail. So we take the unarrowed end, which is the tail, and moves it to the tip of another vector. When we do that, we end up with a triangle, and we can calculate all of the angles in this triangle because of the information we're given. The thing we don't know again, is the magnitude of the vectors TAC and TAB. So we want to find that. So we'll look at it from a geometry perspective. Again, we have our forced triangle. And the main thing we want is this point here, where these two lines aligned with the vectors, or line of action of the vectors, where they cross. So we'll use GeoGebra to find that. Here I have GeoGebra set up with origin already on there. And because the scale is in numbers here, and they're not big numbers, I could shrink it down, but I'll put a point, and I'll use kips instead of pounds. A kip is 1,000 pounds. So I'll put a point at 0 minus 3.5. That is point A. Again, that's the vector pointing down from the weight. And we can name that vector, rename it. We'll name it W, since it is our weight. Now we want a vector going down at 120 degrees through the end of 3.5. To do that, I'll put a line at minus 3.5 again. And then I'll take that line and I'll rotate it. There's a tool here to rotate something, so I'll rotate, select the line, then select the point, and I can rotate it 30 degrees, but I want to go clockwise. So I hit OK, and I've got this new line here, and I'll hide the original line. Likewise, I want a line from the vertical at 2 degrees, so I just make a line, a vertical line, and I'm going to do the same thing here. I'm going to rotate this line about the original point, and I'll rotate it 2 degrees counterclockwise. So I have my two lines now, and what I really want is a point where these two lines intersect. And I can use this tool up here to intersect the two lines, and I'll select one line and then the other line, and I get a point at the intersection. Now that I have the points, that point of intersection, I can draw the vectors from O to this point B, and I'll rename that one TAB because that's really what I'm after. A little fancy typing to make it look neat. I drew it the wrong direction. Oh well. And another vector, and I'll rename that TBC. I may want to move these labels around a little bit. Now I've got the components of these vectors, but I really want the length of the vectors. So what I'll do is type in the bottom here TAB equals lengths and I want to put my vector TAB. So when I hit enter, I'll get my TAB, and rename this one T. And likewise, I'll do TAC equals length of T sub AC. So those are my answers. Again, this is in kips instead of pounds. And this is a geometric view of the problem. Okay, moving on. We'll start using Matlab. But first we'll use the law of sines. You may remember the law of sines as this form: A over sine A, B over sine B, C over sine C. When you use the law of sines, basically you need to know a side angle pair. And if we look at our triangle here, we can see that we know W is 3,500 pounds, so we know one side of the triangle. And we have our 58 degrees. And we got that because we know the sum of the interior angles of a triangle is 180 degrees, so we subtract the other angles and got the 58 degrees. So we know 58, and we know the 3,500 pounds. So I like to rewrite it now as we've got our pair that we know. We know the pair side and we know the pair angle. And we want an unknown side and sine of the angle opposite the unknown side. We can rearrange this by multiplying both sides by sine of the opposite angle. And we get our unknown side equals our pair side times sine of the opposite angle divided by sine of the pair angle. So we'll stick this information, final information, over here, and it's time to bring up Matlab. So the first thing I want to do is define W. Let's go up here. W equals 3,500. I might add a comment there that it's in pounds. Might even add a description, weight of auto in pounds. Now we just want to use our formula here. Let's go for TAB, and that equals the side we know, which is W, times sine D. Sine D is the Matlab command for sine in degrees. And AB, let's see, we want the opposite angle, and the opposite angle to TAB is 120 degrees. And we divide, again, by sine D of the angle we know, which was 58 degrees. And just hitting enter, notice I didn't put a semicolon at the end, so it'll give me my answer for TAB. And I can do very similar with TAC equals, again, the pair side times sine. Now here the opposite angle is 2 degrees. Sine d, 2 degrees, divided by sine d of 58 degrees. And again, just hitting enter, and we've got our answer for TAC. Note that anytime you did a variable or did an operation here, it assigned what was on the right side to the variable named on the left side. And those values show up over here in the workspace. We can also use components to solve this problem. It's useful to break the forces into components, but and we'll use sum of forces in x equals 0 and sum of forces in y equals 0. We can pick our coordinate system, but to start with, I'm going to do x and y as we normally would. When we do that, we end up with sum of the forces in the x direction, and we get TAB pulling to the left, so it is negative TAB, and we do sine because we want the opposite component from the 2 degrees. And we have TAC pulling to the right, so it's positive, and it's cozy here with the 30 degrees, so TACX would be cosine of 30. Sum of the forces in y, we've got TAB times cosine of 2 degrees, gives it a big force in y. TAC is pulling down, and again, at opposite the 30 degrees would be our component vector. And we have W pulling all the way down. We'll rewrite those over here, and I'll show another method, another capability that Matlab has for solving systems. So let's start over by hitting clear. See, and clear console. So we start clear all over again. But I'll still say W equals 3,500 pounds. And a semicolon because I don't need to see it. Okay, I have the equations here, and I'm going to use a symbolic method. And to use a symbolic method, you need to define some symbols. And I'm going to define some symbols, TAB and TAC. This starts the symbolic processor. Note that in my workspace now, these are just symbols. They don't have a numeric value. So I'll do fx for my fx equation, and I'll just type minus TAB. Now in Matlab you can't just leave a space, you actually have to tell it you're multiplying with the star. I want sine d of 2. Again, I'm entering this equation down here. Plus, and TAC times cosine in degrees, 30. Now, this is really an equation, and to indicate an equation in Matlab, or the equals sign, is equals equals, 2 equals equals 0. So now I'm signing fx is now symbolic variable, but it's an equation. And I'll do the same thing for Fy equals TAB times cosine D 2 degrees minus TAC times sine, again, D 30 degrees minus W. And that equals 0. So I've got another symbolic variable, Fy. Again, the symbolic thing is an equation. Now what I want to do is solve the equation, but I want to tell solve what I want for my answer. So I'm going to hit TAB inside bracket and TAC inside a bracket equals solve. And I'm going to put my equations Fx and Fy. And Matlab will work some magic here and give some solutions. Now, let's see, to actually solve it, if we just do TAB, we see we get some big integer numbers because it's tried to solve it very accurately. But I don't really want that, so what I want to do is print it out. And we'll use fprint F as the Matlab command to print things out. And you need a format character %.4 G. The percent says it's going to put in a value there. The 0.4 says it's going to use 4 decimal places, and the G is a general, and we want that's in pounds. And we'll do TAC also, very similar, 0.4%, 0.4 G, and that'll be in pounds also. Now again, that's in quotes, so that's a string, but now we have to tell it what to put where the percents are, and we're going to put TAB in the first percent and TAC in the second percent. I don't need to see the result of this fprint command, but it will still print out the thing. Okay, so there's our result again. TAB is 3,574 pounds and TAB is 144 pounds. So let's go on to another method. We still got our 2 equations and 2 unknowns here, but to do it for a linear algebra, which is what Matlab was originally written for, you want to rewrite this equation in standard form. In standard form, you put one variable first and another variable last, and anything without that variable goes on the right side. Note that sine of 2 degrees, cosine of 30 degrees, and W are all numbers. TAB and TAC are our variables. And to see this in linear algebra, there's some notation. So here's the same 2 equations, and I'm going to rearrange these a little bit. First thing, I'm going to take the variables and kind of move them to the top of the row. Then we'll shift things together a little bit. Now I can group things. So I grouped the numbers. Again, these are all numbers in rows and columns. Now I'll make some space over here, and I'll move my variables down to the side over here, and I'll group the variables also in a matrix. And while I'm at it, I might as well group the right-hand side. Now these things are grouped and organized, and that gives me an equation A times X equals B. Again, it's a matrix equation. It's not a regular equation. And we note that A has the sines and cosines in it. And X has our variables in it. We don't know the value of them yet. And B has our right-hand side. So in Matlab, what we're going to do is define our AX and our B, and then we'll solve it. And to solve that in Matlab, one thing you can do is essentially a special matrix divide on both sides, so that we just have X then on the left side. So this is what we'll want to do. So let's take our AX and B, and we'll bring up Matlab again, and we'll clear it. Clear the console. Once again, W equals 3,500 pounds. Now I need to define the matrix A. So I say A equals, and then a square bracket, and I can just put minus sine D of 2, and then a comma, or a space, cos D 30, and then a semicolon or a return to go to the second row, and enter that, cos D of 2. I like to use commas, sine D of 30, and end it all with another square bracket. I'm not going to put the semicolon there so you can see what this result looks like. And you can see it's all numbers, and they're put in rows and columns. The next thing I need is B equals, and we do the same type thing. We're going to have 0, then a semicolon for a new row, and put W in the row. And we can see B again is all numbers. Now remember, our solution procedure was just to take X and equals A, and then a backslash to indicate this special division B, and hit enter, and we could further set TAB equal to X1 because it's the first row of X, and we can set TAC equal to the second row of X. And we see we get the same values again that we got before. So this is really what Matlab was written to do, and you don't need this for this course, but I thought I'd show it anyway. So we've been using Matlab in statics to solve an equilibrium of a particle with 3 forces on it. I showed a geometric solution or a graphic solution that give me answers in kips, just because I entered it that way. In Matlab, we showed using the law of sines to solve for this. TAB and TAC, and again we get the same results, only in pounds. And we looked at components with x and y. I did a symbolic solution, got the same results, and a linear algebra solution, and got the same results. Again, you can use symbolic and linear algebra to solve simultaneous equations. Got one more method. Remember that we could define our x and y any way we wanted to. So what happens if I define x to be aligned with the rope and y to be perpendicular to that? If we look at our drawing now, our free body diagram, we see that this lower angle is 60 degrees, and the angle between y and TAB is 32 degrees. So if we do our sum of our forces in y, we got 32 degrees times cosine, or TAB times cosine of 32 degrees, minus the weight times sine. Again, sine is the opposite component, and we're looking for y, of 60 degrees. Well, this equation we can actually solve. The only thing we don't know is TAB, so we can solve this equation for TAB. And then we can do some of the forces in x. Again, we get TAB as a negative sine of 32, the opposite side here. The weight is a cozy side on the inside here. The 60 degrees should be cosine of 60 degrees. And TAC is pulling right down the x-axis. And again, the only thing we don't know at this point is TAC, so we can solve this equation for TAC. I'll put those over here and bring up Matlab again. Clear everything out. Clear the console. W equals 3500. And then just TAB equals W again equals W sine D 60 degrees divided by cosine D of 32 degrees. Same number, which is good. Then solving TAC. Now we know what TAB is, so we can just put TAB here. Sine D 32 degrees minus W times cosine of 60 degrees. And we get the same result again. So again, this problem has a lot of ways to use it. I hope I showed you some powerful tools that Matlab has for solving these in different ways. Maybe you'll get used to using them. Again, it's not required at this point. So have a good day.